Before my talk, I'd like to thank the organizers for kind invitation to this nice Munich Center for Quantum Science Technology curriculum. Okay, the title of my talk is Ultracold ytterbium atoms for quantum simulation of Hubbard model to new physics search. Okay, let me first introduce our group members. These people are working very hard for the experiment in this talk. Okay, this is the outline of my talk today. First, I will make a brief introduction of ultracold ytterbium atoms for quantum simulation, including unique features of ytterbium atoms and brief introduction of our recent works. And next, I will describe in detail our recent experiment of a dissipative Fermi-Hubbard model. We successfully observed the same reversal of spin correlation due to the dissipation, and we realized the negative spin temperature. And we also talked about in detail the recent experiment for quantum sensor for new physics. In particular, we performed the high precision isotope shift measurement, and we observed new clock transition. And finally, I will summarize my talk. Okay. And as many of you know very well, our system of ultracold atoms in optical lattice is an ideal quantum simulator of condensed matter physics described by this Hubbard model, owing to its high controllability of important system parameter of hopping T between adjacent lattice site and on-site interaction U when the two occupy the same lattice site. Okay, and the nice feature of this optical lattice quantum simulation is the diversity of research topics. We can, with this system, we can study these important and interesting research topics, to mention a few. Okay, and yeah, for this quantum simulation experiment research, unique ultracold ytterbium atoms offered unique possibility because of some unique features of ytterbium atoms. Okay, and here ytterbium is a rare earth atom with filled 4f shell and 2 valence electrons. So energy structure is similar to that of the alkaline earth atom. Okay, and because of the unique features of ytterbium atoms, this ultracold ytterbium atoms is also useful for precision measurement and also quantum computing, which I will discuss later in this talk. Okay, one of the unique features of ytterbium atom is long-lived metastable state, such as the P0 and P2 state. The lifetime is longer than 10 seconds. So for many applications, such a long lifetime is long enough. 10 seconds is long enough. Okay, and between the ground state, singlet 0, and these metastable states, there are only weakly around ultra-narrow optical transition at these wavelengths. Yeah, and in addition, there are one more ultra-narrow optical transition at this wavelength. Yeah, which associate with the inner orbital excitation of 4f shell, 4f to 5d orbital. So we will discuss this ultra-narrow transition later in this talk. Okay, and these ultra-narrow optical transitions are useful for high-resolution probe of the quantum many-body state, like superfluid multi-insulator transition like this, and free body physics. Our recent high-resolution spectroscopy of atoms in optical lattice, combined with the magnetic reciprocal resonance, revealed that the three-body force in a strongly interacting regime, like this, and we can separately identify the resonance for different occupancy, and we know that this is also the regarded as the quantum simulation of the nuclear three-body force. Okay. Okay, and the existence of these long-lived metastable states is also useful for the study of two-orbital physics. Okay, and one illustrative example is the observation of the orbital Feshbach resonance, like this. And yeah, so in fact, there are many exciting experiments are carried out using this orbital Feshbach resonance. Okay. In more recent work, we use this two-orbital system to demonstrate the novel quantum transport of the ground state atoms in a synthetic dimension of the spin space, which is induced by the localized impurity, which serve as a quantum point quantum. Yeah, so this is a typical example of our measurement of the quantum transport. Okay, and another unique feature of ytterbium atom is rich variety of isotopes. There are 5 bosons and 2 fermions, and in fact, we could generate various quantum degenerate gases like Bose-Einstein condensate, fermi degenerate gas, and their mixture. And the scattering length for each isotope and each isotope pair is precisely determined by our photoassociation spectroscopy. So this is the basis for designing some experiment and for interpreting the experimental result. Okay, and as an example, we demonstrate the formation of the novel dual multi-insulator state of a boson and the fermion, where the boson and the fermion all together form a multi-insulator state with unity fission. This is one example. Okay, and in addition, I would like to note that the rich variety of isotope is also useful for some type of new physics search, okay, which I will discuss later in this talk. Okay, and among many isotopes, fermionic isotope of ytterbium-173, which has nuclear spin 5 Hertz, and so there are 6 spin component is of particular importance because of the enlarged spin symmetry of SU6. Okay, so by loading this ytterbium-173 to optical lattice, we can study the novel SU and Fermi-Hubbard model. Okay, theoretically, these novel quantum phases are predicted at t equals 0. And we think that the possible high TC superfluidity or superconductivity by doping to these magnetic phases is an interesting future research direction, both in theory and experiment. Okay, and along this line of research, we recently studied SU6 quantum magnetism. Yeah, in this research, we performed systematic measurement of spin correlation for various initial entropy for 1D and 3D configuration for SU2 and SU6 system. And these experimental data are compared with the state-of-the-art theory calculation done by our theory collaborators led by Kaden Hubbard in Rice University, and solid line the result of the theory calculation. And you can see that we obtained a good agreement between theory and experiment with no fitting parameters. Okay, and in addition, in the case of SU6 in a 1D lattice here, we can, but through the comparison between the theory and experiment, we can reduce the temperature of the atoms in optical lattice as about 10% of the Hoping T. Yeah, so this is very cold, and yeah, this actually corresponds to the lowest temperature of the cold atom Fermi-Hubbard model, which is realized by Pomeranz cooling owing to the large spin degrees of freedom. Okay, and at these low temperature, interesting quantum phases are predicted, which can be explored by our future experiment. Okay, and in more recent experiment, we extend this spin correlation measurement of the SU6 fermion to various lattice configuration from the isolated pocket to uniform square lattice, and also for various spin imbalance from the SU6 to SU2 cases. Yeah, and in particular, we confirm that the robust formation of SU4 singlet state for the SU6 system. Okay. Yeah. Okay. And as for the diversity of the research topic, recently we studied competition and interplay between the topology of the disorder through the phenomenon of Tower's pumping. Okay, and in our previous work, we used the ytterbium 171, which is almost non-interacting fermion, and we demonstrate the quantization of the Tower's pumping by realizing this dynamical superlattice system. Yeah, and yeah, we realized the particular model of a Rice-Mary model to demonstrate this quantization of the Tower's pumping. And we introduced the quasi-periodic disorder to this clean superlattice system to investigate the effect of the disorder. And here we plot the amount of pumping as a function of the disorder strength, like this. Yeah, as you can see, we observe the quenching of the Tower's pumping by disorder. Okay, and yeah, in addition, our experiments show that the robustness of the Tower's pumping against the Anderson localization, which occur at this weak disorder strength. Okay, and our experimental data can be is consistent with the recent theoretical calculation shown here. Okay, and our experimental results can be regarded, can be interpreted as the localization transition of the Croquet eigenstate, yeah, which is discussed in this theory paper. Okay, and in addition, in this work, we observed another phenomenon of the disorder-induced pumping instead of the disorder suppression of the pumping. And this phenomenon has close analogy with the theoretically discussed concept of the topological Anderson insulator. Okay, we realized this topological Anderson insulator by the Saurus pumping phenomenon. Okay, this is a final topic in the introduction, and recently, in collaboration with Dr. Danshita group, we studied the non-ergodic behavior of 1D Bose-Hubbard model, which is discussed in these recent papers. Okay, and according to this Danshita group paper, in the special initial state of the 1010 state like this, the population imbalance between left and right is dumped to the steady state, indicating the thermalization of this system. Yeah. On the other hand, in the special state of the 2020 state like this, then the imbalance between left and right is freeze for strong interaction, indicating the disorder-free localization induced by interaction. Okay, this is a theory prediction by the Danshita group paper, and these behaviors are actually confirmed by our experiment. Yeah. In the case of 1010, the imbalance is dumped to the steady state of 0, but in the case of 2020, imbalance is free for strong interaction. Okay, and so experimentally, the initial state dependent ergodic and non-ergodic behavior is confirmed. And we know that this has cross analogy with the Hilbert space fragmentation in 1D tilted Fermi-Hubbard model recently studied in these papers. Okay. Now I switch to the second topic of the dissipative Fermi-Hubbard model. Okay, and the system of cold atoms is a closed quantum system, well isolated from the environment. Okay, now if we introduce the dissipation to this cold atom system, then it becomes an open quantum system. Yeah, and the dissipation is usually the source of a decoherence and limit the coherent dynamics of the quantum state. But recently, the novel role of dissipation to stabilize the particular quantum enable state is discussed in this theory paper, and related experiments are reported for particle loss, for light scattering, and so on. Okay, and in our previous work, we studied the dissipative Bose-Hubbard model by introducing the two-body loss by photo association, and we observe the phase coherence of the atoms in optical lattice during the slow quench from the Mott insulated state to superfluid state. And we revealed the novel role of dissipation to stabilize the Mott insulated state in this experiment. Okay, this is a case of a dissipative Bose-Hubbard model, and our recent work focuses on the quantum magnetism in an open dissipative Fermi-Hubbard model, which is discussed in this theory paper by Dr. Nakagawa and his colleagues. Yeah. And the simplest case of the Fermi-Hubbard model is the two-site Fermi-Hubbard model, which can be described by this Heisenberg model for large U limit. Yeah, this is a case of the no dissipation, and J represents super exchange energy. Okay, and if we introduce the two-body dissipation characterized by gamma 2b, then the system can be described by this effective Hamiltonian. Here, J is modified like this, and there is an imaginary term given like this. Okay, And yeah, according to this paper by Dr. Nakagawa, the owing to because of the dissipation, the spin correlation shows sign reversal from the antiferromagnetic one to ferromagnetic one. Yeah, due to the irradiation, due to the two-body dissipation, and this can be interpreted as the selective removal of the spin singlet state. Yeah, and related work on theory and experiment is reported for atom loss behavior, but in our present work, we measure the spin correlation to directly demonstrate this sign reversal behavior. Okay, and in our experiment, we used the SU6 fermions of ytterbium-173 and loaded into dimerized like this. And for the two-body dissipation, we applied photo-association laser beam at this resonance. Yeah. Okay. And initially, the antiferromagnetic spin correlation for various spin pairs created. And after the application of the photo-association laser beam, the ferromagnetic spin correlation is formed. This is a scenario of our experiment. Okay, and for measuring the spin correlation, we use the powerful technique of the singlet triplet oscillation (STO) method. Okay. Written like this, and I'm sorry I will not describe the method in detail, but I will only mention that this powerful method of STO is initially invented by Professor Emmanuel Groff group for rubidium-87 of boson, and later applied to the fermion by Etihad group, and we extend this method for SU6 or SUN fermions. Okay. And this is a typical STO signal of SU6 fermions. And we fit this experimental data with this function. And from this fitting, we can deduce the important quantity of spin correlation of normalized STO amplitude A, and also the singlet fraction and triplet fraction, like this. For detailed derivation, please see these papers. Okay, and we are working with 6 spin components. So there are many various spin pairs. So, and we confirm that the photo association lines used for introducing the dissipation, and also photo association line used for STO method are active for all spin pairs with almost no spin dependence. Yeah, right. Okay. Okay, and this is the main result of this experiment. And here we plot the spin correlation as a function of the irradiation of the photo association right. And here I also show that the STO signal at this time, okay, and you can clearly see that the sign reversal of the STO signal, which means the sign reversal of the spin correlation. Okay, and we perform the experiment with 3 different initial conditions with different antiferromagnetic correlation. And for all these 3 cases, the spin correlation changes from the initial antiferromagnetic one to ferromagnetic one. Okay, and we also confirm that the sign reversal of spin correlation is actually induced by the selective removal of singlet fraction and the triplet fraction is kept constant. Yeah, this is consistent with the theoretical scenario. Okay, and sign reversal of the spin correlation means sign reversal of the spin temperature. So spin temperature is defined like this, and yeah, as you can see that initially the spin temperature is positive, and it goes to infinite, and it goes to negative. Yeah, like this. Okay, and we also investigate the spin correlation in the presence of a dissipation for various lattice geometry from the isolated double well to 1D uniform lattice like this. For all lattice configuration, we observe the ferromagnetic formation of the ferromagnetic spin correlation, okay, like this. And in particular, we observe the ferromagnetic spin correlation in a 1D uniform lattice. Although it is small, but anyway, we observe the finite ferromagnetic spin correlation, which indicates the formation of a Dickey type ferromagnetic spin correlation in this system. Okay, and our future work includes a study of the dissipative Fermi-Hubbard model, which is specific to the SUN system discussed in these recent theory papers. Okay, okay, and now I switch to the second topic of a quantum sensor for new physics. Okay. Okay, the background of this research is quite different from the first one. Okay, and as you know that in elementary particle physics, there is a theory known as the standard model, which provides excellent explanation of the most of the phenomena in nature. Okay, but standard model is anyway empirical model, and it cannot explain some of the important phenomena like dark matter or dark energy and so on. So there has been a considerable effort for searching for physics beyond the standard model, from the high energy frontier to a low energy precision measurement. Okay? And in the approach of the low energy precision measurement, and these recent papers attract much attention. Yeah, these papers propose that searching for a new boson mediating a force between neutron and electron through precision isotope shift measurement. Okay, and the mediated force between electron and the neutron is written in a form of a Yukawa force like this. And here, M is the mass of the new boson, and YE and YN is the coupling constant between the new boson and electron and the neutron respectively. And S is the spin of the new boson. Yeah, and in general, the isotope shift between the isotope pairs of mass number A prime and A for the specific optical transition lambda can be described like this. Yeah, here the first term is called the mass shift related to the reduced mass, like this. And second term is called the field shift, coming from the Coulomb interaction between the electron and the charge distribution inside the nucleus. And third term is its higher order term. Okay, and if there is a new boson mediating a force between neutron and electron, we have one more term of a new particle shift, which is proportional to the mass number difference, or in other words, neutron number difference. Okay, and so in principle, the isotope shift data include contribution from the possible contribution from the new particle. Yeah, but these nuclear factors are very difficult to evaluate theoretically at the current precision of the nuclear theory. So the direct comparison between the theory and experiment for isotope shift is hopeless to get some information about the new particle. Yeah. So then any solution? Yeah. The one possible solution is the King-Prot approach. Yeah, known as the King-Prot approach. Yeah. Instead of considering the one isotope shift of one particular optical transition, we consider the isotope shift for 3 different optical transitions like this. Okay, and from these 3 equations, we can remove the 2 unknown nuclear factors. Then we get the one linear relation known as the King linear relation. Okay, so if we plot the isotope shift data for in a 3 dimension corresponding to the isotope shift for 3 different optical transitions, then all isotope shift data should be aligned in a plane like this. Yeah. So possible deviation of the isotope shift from this plane or nonlinearity of the King linear relation can be considered as a signature of a new boson. Yeah. This does not require the precise knowledge about the nuclear factors like this. But still, we can say something about the possible new physics from this isotope shift measurement. Yeah, for this experiment, the large number of isotopes is advantageous in this approach. So we perform the precise isotope shift measurement using ultracold ytterbium atoms in optical lattice because there are many isotopes for ytterbium atoms. Okay, and we prepare the ultracold ytterbium atoms and loaded into a 3D optical lattice with magic wavelength. In the magic wavelengths, the right shift for the ground state and excited states are the same. So the resonance frequency does not suffer from the right shift effect. And this is a typical spectrum we obtain. The line width is about 10 hertz or less. Okay, and a little bit more details of our experiment are written here, but I try to skip this. And I also skip these very important, careful evaluation of the systematic uncertainty and corrections. And I will tell you the final result. And we determined the 5 isotope shift with a few hertz uncertainty and corresponding to the parts per billion uncertainty. Yeah. So this is not bad. And particularly, we achieved comparable precision with the previous state-of-the-art optical lattice plot result for these isotopes reported by me. So yeah, it's good. Okay, and our precision isotope shift data is used to construct the 3D King plot like this. Yeah, and investigate some possible nonlinearity. And for this construction of the 3D King plot, we use the isotope shift for other transition reported by MIT for ytterbium ion for these two optical transitions. Okay, and yeah, the isotope shift data are actually around in a plane mostly, but if we look at carefully, we have a definite deviation from the linearity, and this corresponds to the non-linearity of the 3 sigma level. Yeah. So this observed non-linearity can be a signature of the new particle. But we consider one more higher order field shift known as the quadratic field shift as the main cause of the observed non-linearity. And within the uncertainty, we set the upper bound of the new particle. Okay, this is the result of the determination of the upper bound for new boson obtained in such a way. And here we plot the coupling constant as a function of the mass of the new particle. Yeah, in this plot, in this determination of the upper bound, we use the more recent results reported by MIT group corresponding to the WS to WF 7 state of the ytterbium ion. Okay, and our bound is close to the terrestrial bound set by the electron G-2 and the neutron scattering. And yeah, so it's it's nice, but we think that we can improve the limit by reducing the uncertainty for all of these 3 transitions, not only one. Yeah. So in this respect, recently the precision isotope measurement for other neutral ytterbium transition and also improved results for ytterbium ion reported quite recently. So yeah, this is quite a hot topic, I think. Okay, and to improve the precision of isotope shift measurement, we need more ultranarrow transition for ytterbium atoms. So as I mentioned in the introduction, there is another ultranarrow optical transition at this wavelength associated with the inner orbital excitation like this. Okay, and this transition is theoretically predicted by these papers. And these papers predict the lifetime of about 200 seconds. They're really wrong. And so natural line of this should be quite narrow. And this is good for precision measurement. In addition, this ultra-narrow transition and or J-2 state is very sensitive to several kinds of new physics, such as the time variation of fine structure constant, or violation of the local Lorentz invariance, and new boson mediating a force between electrons and neutrons. So it is useful for isotope shift measurement. So we started searching for this interesting new crop transition. And after several months of search, we finally observed this transition. Okay, and for this search, we used evaporatively cooled sample of ytterbium atoms in a closed dipole trap, and we radiate laser light, frequency stabilized laser light at this wavelength, and we observed the loss of the atoms in the ground state due to the resonant excitation. And this is a typical spectrum we obtain. And in the case of 124, and there are 5 magnetic sublevels like this. And yeah, we observed all of these resonance corresponding to the 5 magnetic sublevels. And for other isotopes, we also observed similar like this. Okay, and we revealed the basic properties of this ultra-narrow optical transition, like G factors or isotope shift between bosonic isotope pairs and hyperfine constants of the fermion isotopes, and also the lifetime. The theory predicted about the 200 seconds at the lifetime, but our measured value is about 2 seconds. Probably it's limited by the background gas collision or light scattering, but the 2 second lifetime is already long enough for many applications for precision measurement and quantum simulation. Okay, and one crucial issue for the precision measurement or also quantum simulation is the existence of magic wavelengths. And we discovered magic wavelengths for this new crop transition for various conditions for wavelength range here and here. So this is the summary of the observed magic wavelengths like this. Okay, and yeah, magic wavelengths definitely exist for this new crop transition, and so by working with these magic wavelengths, we can perform the high resolution spectroscopy for searching for new physics. Okay, and this is a summary of my talk. And for the first part of my talk, we reported the study of the dissipative SU6 Fermi-Hubbard model, and we observed the sign reversal of the spin correlation from antiferromagnetic one to ferromagnetic one by the dissipation. And in the second part of my talk, I reported the high precision isotope system measurement, and also reported the observation of the new crop transition. And before the end of my talk, I'd like to briefly report on our recent effort on the ytterbium atom-based quantum computing. And there are many advantages of ytterbium atoms for quantum computing. This morning, I know that there are many interesting projects here using the strontium atoms. And yeah, some of the advantages common for ytterbium and strontium. Okay, and yeah, in the case of ytterbium, there is a 171 ytterbium of a fermionic isotope, which has a nuclear spin 1 Hz. So it provides a robust qubit based on the nuclear spin degrees of freedom with long coherence time. And as I mentioned, there are long-lived metastable state. And from this metastable state, we can perform a single photon Rydberg excitation, which would be useful for high fidelity 2-qubit gate. And also some of the Rydberg states can be optically trapped owing to the existence of the one more valence electron. Okay. There are many other advantages with ytterbium atoms and also our strontium atoms. And this is our current setup. And we use the SLM for producing the optical tweezer arrays through high NOA objective lens. And we observe the fluorescence at 399 nanometer right, while the atoms are cooled in a tweezer array by this intercombination line. And so far, we tracked the single ytterbium atoms in optical tweezer array, like with these various lattice configuration. And we are now working with the Raman sideband cooling, formation of the defect-free array by rearrangement, single atom nuclear spin Ramsey signal, and Rabi oscillation. So further efforts are now underway in our lab. Okay. Thank you very much for your attention.
Okay, I'm sure there are many questions. Yeah.
Yeah, thank you for that nice talk. I was wondering regarding the new physics model for new boson. So it isn't quite clear to me. Are you also sensitive to test on spin independent force, or how does the spin dependency enter into the proposed model for this new boson? Because to what I know, one typically distinguishes between spin independent and spin dependent forces for such a new boson.
Oh, yes. You mean that yeah. So bosonic isotope has no spin degrees of freedom, and so yeah, that is in the measurement. But the force itself is you mean this new force could be spin dependent for new boson or electron or neutron. So far, we don't consider the spin dependence of the electrons or neutrons, but it depends on the spin of the new boson. Just only the spin dependence we consider.
So this model assumes a coupling between electron and neutron.
That's right.
But why doesn't the coupling between electron and proton enter?
Yeah, this is a hypothetical particle, hypothetical new boson only mediate the force between neutron
Okay, so you're kind of
electron. Yeah. It is also sensitive to the proton, electron, and proton. Then the isotope shift measurement. No. Yeah, it's just yeah. Does not consider the interaction between the proton and the electron. Yeah.
Thanks.
Yeah, this is just a hypothetical particle.
Okay, so I'm interested about the last part on the quantum computing you showed. So, and you presented this new line, the ultra narrow transition of 431 nanometers. Do you think, or do you envisage any application for quantum computing or this very narrow transition? Now you said 2 seconds, but maybe you said maybe now it's only limited by lifetime of atoms. Your experiment.
Yes, we are considered as another Here we can also consider the another long-lived metastable state for J equals 2 state, but the Rydberg it's in principle possible to perform a single photon Rydberg excitation using starting from the J equals 2 state, but we estimated the wavelength for single photon Rydberg excitation is deep in UV. So I don't think it's realistic to use the J equals 2 state as the starting point of the Rydberg excitation. Yeah, but
Right, but now you have this other ultra narrow transition at 431 nanometer that you mentioned. That's
yes. Yeah.
Okay, that's what you drew now here.
Yeah. Here we only consider the to be P2 or to be P0, but yeah.
This is
not the 431 transition. 431 was different transition.
This was a different one, right?
That's the quadrupole
Exactly.
transition.
So because
that's the normal quadrupole transition. This is the 431 is completely different one.
Yeah, so I was thinking whether this you can use it for shelving or any other application for quantum computing, because I didn't see this drawn in the other diagram on quantum computing.
Yes, yeah, maybe, yeah, for shelving it will work. Okay, yeah. But for readable excitation through this state, the wavelength is not easy to use. Yeah, that is not good. Yeah, but yeah, in principle, yes, can be used for sharing.
Okay, more questions? Immanuel, you want
Yes, it's great. Thanks for this very nice talk with this many results. Two questions, so maybe on this one first. So this was done in a 3D lattice or the 1D lattice where you found the clock, magic transition rate?
Yeah,
and you have to.
Yeah, this is done with the
across
the dipole trap.
Just cross dipole trap, no lattice at all in this.
No, not yet. The only lifetime measurement is done with the 3D optical lattice to isolate the atoms. Yeah, otherwise atom collision.
Exactly, it should be collisions between the excited state atoms, right? That limit your lifetime.
Yeah, so that we perform the measurement of the lifetime in atoms in a 3D lattice. Yeah.
So what line width did you measure on this transition already on this 431?
Yeah.
How narrow was the line you could see so far with the?
Yeah, it's about 32 kilohertz. It's limited by the Doppler broadening, and also we are not for this measurement. We are not working with the magic wavelengths. So there is some inhomogeneous broadening,
right.
But we are now preparing the magic wavelength lattice to obtain a very narrow remedies.
We have another question on the dissipative Hubbard systems that you had. You were calling this the Dicke type ferromagnetism. Can you explain a bit more why you call it Dicke type?
Yeah.
Or?
Theoretically, the 1D atoms in 1D lattice with had a Dicke type spin correlation with so Dicke state is has a largest spin paramagnetic correlation. It's a really entangled state. But in the case of a double wave lattice, we only consider two atom entanglement. But in a Dicke state, all the atoms in a 1D lattice is entangled to form a highly non-classical state of the spin state. Yeah. So the Dicke state has a paramagnetic spin correlation. So our observation can be linked to such a Dicke type spin correlation. Yeah. But of course, we did not directly measure such a highly entangled spin correlation in our measurement. We only measure the nearest neighbor spin correlation. But it's it indicates the sum of the Dicke type spin correlation. Yeah.
So if you would have a quantum gas microscope, what would you see, or what would you measure?
Yeah, maybe. Yeah, it's you can identify the Dicke type spin correlation in a quantum gas microscope. Yeah.
But what's actually the filling fraction in these lattices?
Yeah, it's a we don't know right now.
But roughly like close to 1 or very small?
Um,
In number patterns perspective.
Initially, it's typically one particle parts one side, but after the dissipation, it should be smaller. But there is a harmonic confinement, so yeah, at the center of the trap, it should be larger, but yeah, we don't know.
I think there was questions over there.
Maybe a bit naive, but what was that terrestrial bound you were showing on the new bosons bounds? Yes.
Okay. Our bound is marked with pink, and the orange line is the bound set by the terrestrial bound of the electron G-2 and the neutron scattering data.
Combined?
Combined,
Okay.
yeah. So it's coupling constant is the product of the electron YE and the neutron YE. So, yeah.
Okay.
So, yeah.
Thank you.
Any more questions?
So, why is it actually slightly different than the plot from your paper? So, I mean, is it?
Yeah. We use the more recent data by MIT for different transition. So
Okay.
yeah, in this paper we use different transition.
Okay.
At this time, we don't know the newest data.
Okay. And so you're using this.
Yeah,
So which data are you quoting again for the newer plot?
Yes, we use the shift data for alpha transition for ytterbium ion and beta transition for ytterbium ion and others. This is a transition used in this paper, but in this plot we use our data and one of the transition and new isotope shift data for WTS to WTF transition.
Okay.
So this is the difference. Yeah.
Okay. Thanks.
Yeah, I actually had a quick question on the dissipative Hubbard systems again. So you were showing basically that you can use two-body loss to stabilize a mod insulator in bosons. If I understand correctly, why this happens is basically because you have xenotype suppression of the quantum fluctuations that drive you into a BC or superfluid ultimately. So first question, is that the correct picture? And second, do you actually have atom loss when this occurs, or is it actually happening, let's say, just without atom loss, and you could even like turn off the dissipation and then do a standard ramp down in the BC? So maybe first question, is this picture correct that what happens here is a suppression due to xenodynamics of the quantum?
For the first question, quantum zero effect is responsible for the stabilizing the multi-insulator state. Yeah, and with strong dissipation, the hopping is suppressed. That's why the atoms are localized, stabilizing the multi-insulator state. Yeah, that is our interpretation of this phenomenon.
And so, do you observe atom loss in these experiments then?
Yes, we observe the atom loss. Yeah, and we also calculate the atom loss behavior theoretically and compared with our experiment, and we find agreement between theory, including the atom loss behavior. Our observation is consistent with our the theoretical interpretation, calculation.
Could you do a transport measurement? Because if you go, in an antiferromagnet, charge transport should be really hard. But then if you're ferromagnetic, the charge should have a very easy time to move. So would be interesting to see how the loss affects charge transport measurements actually.
You mean not only measure the spin correlation, but also some transport.
Yeah.
Okay. Yes. Yeah. Maybe some type of lattice geometry. Maybe we can measure some transport phenomena. Yeah.
More questions? Okay, I do want to, is it really the new boson or does it have a real name? Yeah.
Name.
You just call it new boson so far? Nothing.
Yes. No one name.
All right.
Some
Good
name.
Okay, so thanks again for a great talk. Genau.